Hi, in this lecture we'll be talking about measures of dispersion. I'll introduce the topic and discuss some measures of dispersion, and we'll continue the discussion in the next video. Let's go back to Ronaldo. Remember this picture? Now, we said here the central tendency, since almost everyone is looking at Ronaldo, we said the central tendency in this picture is Ronaldo. Therefore, we tag the picture Ronaldo greeting his fans. But we also noticed that there were some people who were walking away. And these people are definitely looking towards Ronaldo, but their attention is not entirely on Ronaldo. So, by describing the photo to be fans of Ronaldo, we are accounting majority of people in this photo, but there are some whose attention is elsewhere. How do we measure that? And that's what measures are dispersion for. Before we proceed, let me give you a more realistic example. If you conduct a quiz or an exam or a survey in Google Forms, they'll show you the summary as this. On top, in Summary tab, you'll be shown some insights. The first two insights are average, which is nothing but referring to arithmetic mean, and then median, which is what we discussed earlier. Positionally the central, mathematically the central value is average, positionally the central value is median, and there's a small problem. It says average is 20 and median is 22. That means there are different values, and there is value 22 for sure, and there are some values less than 22 for sure, less than 20 in fact. But what's the minimum value? Who performed the weakest in the class? Did someone score 0 points, or did someone score all points, maximum points, 34? We don't know that from these central values, right? The central values are definitely helpful but not really insightful. In that case, we'll have to use the next information given in Summary tab. That's range. What is the minimum and maximum value? Now I know that nobody in the class did really bad in the exam, and some did really good, but no one scored all 34. So measures of dispersion, how dispersed or spread the data is, gives us more insight into the data we are looking at. In fact, if you see the distribution here, point distribution, you can see that two people scored 26, one person scored 12, which is the minimum, and 26 is the maximum, and two people scored 24. So it is dispersed, distributed. Just by looking at central tendencies, we were not able to make much conclusions. Range gave us better insights. That's a need for measures of dispersion. How distributed our data is. For example, look at the numbers 1, 0.5, 0.25, 0.125. These numbers are all very close, right? While if you look at 1, 10, 40, 600, etc., they are too far away. How do you quantify this very close and too far? That's our question here. There are some tools to do that. And before we get to the list of tools, let's look at the requisites for ideal measures of dispersion. Remember, we had a similar discussion about ideal measures of central tendency. This is almost the same. In fact, the first condition is that it should be easy to calculate and simple to follow. Remember, that was the same first condition we had in central tendencies. Second condition is that it should be rigidly defined. And third condition says that it should be based on all observations. Fourth condition says it should be useful for further mathematical treatment, and in the fifth condition, we assure that our values are not affected much by fluctuations of sampling. There are two kinds of measures of dispersion, absolute and absolute measures of dispersion. We will be discussing our range, quartile deviation, mean deviation, standard deviation, and variance. while relative measures of dispersion are coefficient of variation. And there are many other relative measures of dispersion, but our concentration will be on coefficient of variation. Coefficient of variation is calculated based on standard deviation, and that's why it's called relative measures of dispersion. Let's start our discussion with range. Range is the easiest measure of dispersion. So to calculate range, you simply have to subtract the minimum value from the maximum value. Suppose B is the greatest observation and A is the smallest observation. Subtract them. Note that we'll be looking at the observations and not the frequencies. So it's fairly easy to spot range or calculate range. Let's do some examples. In the first problem, the distribution is 1, 5, 21, 4, 1, 6, 11. And we can easily spot that the maximum number is 21 and the minimum number is 1. So range is equal to 21 minus 1 is equal to 20. In second question, again, you see that there are somewhere around 50 or 60 observations. But if you look at this, you have to simply look at the values in observation, and in the values the maximum is 6 and minimum is 1. Therefore range is equal to 6 minus 1 is equal to 5. Easy, right? Here's another example. Here the numbers are really big. There are too many numbers as well, but we can simply by observation spot that the minimum value is 9, maximum value is 200. So range will be equal to 200 minus 9 is equal to 191. Note that in this particular distribution, in the frequency tables given to us, both of the cases, we simply looked at the values. We didn't look at the frequency of the values. So that's how we calculate range, and it's fairly easy to calculate range since it involves only two numbers in the entire distribution, and those two numbers are not too hard to spot. How ideal is range? Is it easy to calculate? Totally. It's absolutely easy to calculate and fairly simple to follow. What about definition? Yes, it's rigidly defined. We know there will be one minimum and there will be one maximum value, so no issues. But unfortunately, it is not based on all observations. It uses only the two extreme values, and since it uses only the two extreme values, it's useful mostly for small data sets. If your data set is too big, say 1000 or 2000 values or even 100 values, range might not give you really good insights. When it comes to further mathematical treatment, since it's rigidly defined, it is suitable for mathematical treatment, further mathematical treatment. But since it's not based on all observations, I'm a bit doubtful about the insights it can give you. That same applies to the fluctuations in sampling. Since it's simply based on the maximum and minimum value, if the value is fluctuating, range might not perform that well. The next measure of central tendency is quartile deviation. To calculate quartile deviation, we need something called quartiles. As the name suggests, it is something to do with quarters. So what we would do is, we'll take the distribution, find the value in the quarter position. Remember median? Median was the number or the value in the center. In this case, quartile deviation, to calculate quartiles, we are finding the quarter values. Median was the n by second value. Here, first quartile is the n by fourth value, and third quartile is the 3n by fourth value. It's almost like you have a distribution. Value towards the center is your median, and value at quarter distance, something like from beginning to center, the value towards the quarter distance is your first quartile Q1, and then from middle to the last number, value towards the center of this gap, or 3/4 distance from beginning, is your third quartile. Interesting. So to find quartiles, first quartile, we are considering the values before it, that is, and to find third quartile, we are considering the values after it, or we can calculate it using the values between median and quartile. So we are at least considering 50% of the values here in case of finding quartiles. And quartile deviation is given by arithmetic mean of first and third quartiles. So we are considering 25% of the values here to find third quartile, 25% of the values here to find first quartile. So to find quartile deviation, we are in total considering somewhere around 50% of the values. Another interesting observation is first quarter is called first quartile, third quarter is called third quartile. What could be second quartile? In some books you will notice that median is called the second quartile because n by second value or 2n by fourth value is nothing but the median itself. Let's take a look at an example. You can easily spot that in this particular distribution you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 numbers. So total number of observations is 11. Maximum value here is simply 11. Since it's already sorted, just pick the biggest number. Minimum value is 3. Just pick the smallest number. Now, range is maximum minus minimum, and that's 8. Median can be found by one of the ways is find 11 by 2, and then 11 by 2 will be somewhere around 5.5. The integer just above 5.5 is 6, so in the 6th position you have number 6, and therefore median is 6. Or in simple terms, just look at the entire distribution. You can easily see that the value towards the center is 6, and therefore median is 6. First quartile can also be found by finding 11 by 4, which will be something like 2 point some value. Integer just above 2 point some value is 3, so number in the third position, or simply consider the numbers from beginning till median. Number towards the center is 4, and therefore our median will first quartile will be 4. Similarly, you can easily spot that 3n by 4th value will be the 9th value, which happens to be 9 itself. Now, we have calculated first quartile and third quartile. Quartile deviation is the arithmetic mean of third and first quartile, which is nothing but 13 by 2 is equal to 6.5. Fairly easy to calculate, right? So this deals with the maximum, range deals with the maximum and minimum, quartile deviation deals with quarter values and their average. Let's take a look at another example, and in this example we are given a frequency distribution. So to find n by 4th and n by 4th and n by 3n by 4th value, we obviously need to draw a cumulative frequency table like we did for median. To do that, I have drawn the table. Let's fill in the data. X takes value from 1 to 5 in this case, and it has frequencies 7, 10, 11, 4, 8. The cumulative frequencies are calculated, if you remember. In the first row, we simply copy the frequency of that row. The second row, we add the cumulative frequency of the previous row plus the frequency of that row. Here, 7 plus 10 is equal to 17. Third row, 17 plus 11 is equal to 28. Fourth row, 28 plus 4 is equal to 32. In the last row, you have 32 plus 8 is equal to 40. And if you remember, we told that the cumulative frequency of the last row in the table will be the same as total number of observations. So let's go ahead and calculate. Total number of observations is 40. N by 4 is 10. 40 divided by 4 is equal to 10. 3n by 4 is 3 times n by 4. Here n by 4 we got it as 10. So 3 times n by 4 is 30. So just like we did for median, find the row with cumulative frequency just greater than 10. In this case, 7 is less than 10 and 17 is greater than 10. So n by 4th value for the first quartile is the corresponding value of x, and that's 2. Now, 3n by 4th value, or the third quartile, is to find third quartile, we have to find cumulative frequency which is just above 30. Cumulative frequency just above 30 is 32 here, and corresponding value of x is 4. So the third quartile is 4. Thereby, you can find the quartile deviation as 4 plus 2 by 2, the average of first and third quartile, and that is 6 by 2 or 3. It was fairly easy to calculate, right? In fact, if you look at how ideal quartile deviation is, in case of range, we gave range 2 out of 5 points. And the last 2 points we didn't consider because it is ideal for further mathematical treatment and it doesn't get affected by fluctuation, but that's not actually a power. That's basically because it doesn't mind about any other values than the first and the last value. Let's see if quartile deviation is an improvement from range. Obviously, it's fairly easy to calculate and simple to follow, and it is rigidly defined for sure because it is using quartiles. And then, is it based on all observations? Not exactly. It uses 50% of the values, which is definitely a step up from range, but there is another 50% it is ignoring. Hence, it's not based on all observations. That's why I gave it an orange color. Now, since it doesn't take care of all the values, it ignores some values in between, we cannot say it is the best for further mathematical treatment or if it is affected little by fluctuations of sample. So again, range got 2 out of 5. Quartile deviation is a slight improvement. It has got 2.5 out of 5 points. Can we have a better measure of dispersion? The answer is yes. Meet mean deviation. Mean deviation is a way to calculate how far away is it from the mean. And the mean can be arithmetic mean, median, or mode. It can also be geometric and harmonic means. So mean deviation calculates how distributed is the data away from the mean value we calculated. Now, calculating mean deviation, we use this particular formula. 1 by n into summation frequency into observation minus the mean we are considering. Absolute value of that number you get. Absolute value, I hope you remember what absolute value is. It's simply absolute value of minus 3 will be 3. You are just ignoring this minus. Absolute value of any negative number will be the number without the negative sign. Absolute value of any positive number will be the same number, and the toughest of all, absolute value of 0 will be 0. So we use to calculate mean deviation, we make use of absolute value. Let's try an example. We are going to find mean deviation of that distribution about median. So to find that, we need to apply this formula. And turns out to apply this formula, we need to first find the median. Simply by observation, we can find that the median is 6. The value towards the center positionally. And we have to assure, before you spot the median, you have to assure that the value is sorted. And turns out, luckily in this case, the values are sorted. Now, to calculate mean deviation about median, first we have calculated the median. One step done. We have to calculate each observation minus the median, and then we have to find the absolute value, and then we have to find frequency into the absolute value, and at last add them all up to get this summation. Remember, in such situations what we did in the problems before, we will draw a table. In this table we have found our median here, so no issues. Then we have to find each observation minus the median, so our first column will be xi's, second column will be frequencies, third column should be xi minus the median, fourth column should be absolute value of xi minus the median, fifth column should be fi into the absolute value we found. Sum of the rows in fifth column. So sum of the fifth column will give you the entire summation. Let's go ahead and draw the table and finish the calculation. So the first column we have x, second column you have frequency, third column we have x minus the median, fourth column you have absolute value of x, x minus median, fifth column frequency into x minus median. Let's fill in the data. You have 5, 6, 8, 9 and 11. 5 has the frequency 3, 6 has frequency 1, 8 has frequency 1, 9 has frequency 1, 11 has frequency 1. X minus a, here a is equal to 6. So 5 minus 6 is minus 1, 6 minus 6 is 0, 8 minus 6 is 2, 9 minus 6 is 3, 11 minus 6 is 5. Absolute value of this column is 1, 0, 2, 3, 5. Again, frequency into absolute value is 3 into 1, 3, 1 into 0, 0, 1 into 2 is 2, 1 into 3 is 3, 1 into 5 is 5. Adding the last column, we have 3 plus 2, 5, 5 plus 3, 8, 8 plus 5, 13. Total number of observations is 7. You can either add up the frequency or you can simply observe here since the distribution is fairly small. So n is equal to 7. and mean deviation about median will be 1 by n into summation f into absolute value of x minus median, which is 13. So 1 by 7 into 13, and in fact once you do the calculations you'll find that this value is equal to 1.9. Not too hard to calculate. You had to draw a table and it was a bit more hard to calculate than possibly quartile deviation, but not too impossible. In fact, as an exercise you can try to find mean deviation about other averages like arithmetic mean or mode. Mode of this distribution is 5. So try to find mean deviation about mode. Try to find mean deviation about arithmetic mean. You will find something interesting there. Mean deviation about median, we got it as 1.9. Mean deviation about mean, which is arithmetic mean, you will get it as 2. And mean deviation about mode, you will get it as again 2. Interesting, right? So if you look at these three values, you'll note that mean deviation about median is the smallest. In fact, in given any distribution, mean deviation about median will be the smallest number compared to mean deviation about other averages. Interesting. In this particular case, mean deviation about mean is equal to mean deviation about mode. But that's not the case always. You may have different values as well. But no matter what, mean deviation about median will be the smallest among all the other mean deviation about means, averages. Another interesting observation is that mean deviation about any average will always be positive. The trick is in the fact that if you add positive numbers, it will always be greater than 0. Here we are adding frequency, positive number, absolute value of any number is positive, so positive into positive, so sum of positive numbers, and hence this will be always positive, greater than or equal to 0. So mean deviation about any average is always non-negative, positive. In fact, when will it be equal to 0? That's a good question you can ask. For that, as an exercise, you can try to find mean deviation about mean, median or mode of this distribution. That is, I randomly chose 5. You can choose any number you want, but all the numbers are same in the distribution. In this case, try to find mean deviation about mean, median, mode. You will find that that value will be equal to 0. So that's why we had to include the case that mean deviation about any average will be greater than or equal to 0. How ideal is mean deviation? We gave range a 2 out of 5. We gave quartile deviation a 2.5 out of 5. And is it easy to calculate? It's not too hard. In fact, it is the most complicated so far, but still it's easy to calculate. It's rigidly defined. Well, it is. Well, it has a mathematical formula and rigidly defined. It's based on all observations because we are considering all the values of x in the formula for median. And when it comes to further mathematical treatment, there's a small problem. As I told you, we are taking absolute value in our formula. An absolute value has limitations in further mathematical treatment. So it is useful It is rigidly defined, and it overcomes the problem with quartile deviation and range, that it is based on all observations, but yet because we use absolute value to make the mean deviation positive, it is not really useful for, really suitable for further mathematical treatment. And it has agreed for possible fluctuations of, considering the possible fluctuations of sampling into the final value we get. So at the end of the day, mean deviation is definitely a huge jump from quartile deviation and range, and we have a 4.5 out of 5. Can there be something better than this? That'll be our topic of discussion in the next video.